Hello everyone and welcome back to another mathematics tutorial. Today I'm going to be teaching you about metric spaces. I'll give you the definition of a metric space and give you some examples of types of metric spaces that you may encounter. Now I've got part of the definition here on the screen for you. It says that a metric space is a pair, MD, where M is a set and D is a function from M cross M to the real numbers such that means we're going to have some conditions holding. So I'll write these conditions down for you. So condition number 1 is that for every xy in M, d of xy is greater than or equal to 0. So it's always non-negative. Condition number 2 is that for every xy in M, d of xy is equal to d of yx. So it's symmetric. Okay, d of xy is d of yx. Condition number 3 is that for every xy in M, d of xy is equal to 0 if and only if, so this if with two f's means if and only if x is equal to y. Okay, so this d of xy will be 0 only when x is equal to y. And finally, condition number 4 is that for every x, y, z in M, so we have 3 points now, every x, y, z in M, we have d of xy is less than or equal to d of xz plus d of zy. So essentially this z is an intermediate point, and you want d of xy to be smaller than or equal than going via this intermediate point z. Okay? So that's for every x, y, z in M. Now if all of these conditions hold, we call M a metric space, or the pair MD a metric space, whichever you like. Now, what is the point of all of this? Well, the idea is that this is supposed to be an abstract notion of distance. Okay, so it's supposed to be an abstract notion of distance. So M is some set, so this is our M, some set, and we have some points in M. Okay, so we have a point X and we have a point Y. And D is supposed to give us the distance from X to Y. Okay, so D gives us the distance from X to Y. Now, this distance might not be the normal kind of distance you're used to. It can be any notion of distance that satisfies these conditions. And I will be going over some examples of different types of distance that do this sort of thing. Now, let me just illustrate each of these points. Distance we want to be non-negative. That would make sense. I mean, we don't want a negative distance going to somewhere. You know, it can't be sort of minus 2 meters tall or something. So we want it to be, you know, non-negative always. Then we also want it to be symmetric, condition number 2. So going from x to y is the same distance as going from y to x. Then we want it to be 0 only when we're looking at the distance from a point to itself. That makes sense. I mean, if you're at x, then if you don't go anywhere, then you want your distance to be 0. And condition number 4 is if you have a third point, z, so this is our third point, then going from x to z and then to y is going to take you longer than going just straight to y from x. So that's essentially the triangle inequality in a more abstract form. Okay, now I said I'd give you some examples, and I intend to make good on my promise. So the first example we're going to go over is going to be one you're familiar with, I would hope, and that's going to be the case of the real numbers. So we're going to take M is equal to R, the set of real numbers, and D of xy is going to be the modulus of x minus y. So it really is the distance from x to y in the usual sense that we're used to. Now it's very fairly easy to check that these definitions here, this M and this D, satisfy the conditions that we just talked about in the previous slide, or the previous section. So 1, what is 1? Well, 1 is the distance from x to y has to be non-negative, and certainly modulus x minus y is greater than or equal to 0, certainly. That's just by definition of the modulus function. Condition number 2, well, we need it to be symmetric, and certainly we have this being true, and then that is clearly just y minus x, so certainly this is true, so both of these are true. Condition number 3, well, this is this being equal to 0 thing, and if this is true, then that implies that x minus y is 0, and then that implies that x is equal to y. So that one is certainly true. And then number 4, well, this is just the triangle inequality. So if I rewrite this using z here, then certainly this is less or equal than modulus x minus z plus modulus z minus y. Okay, so we're good. We have proven all 4 conditions are true. I encourage you to go through this yourself and make sure you understand this, because it is very important to understand this definition. So that's a fairly easy example. And this may make you wonder, what's the point of all these metric spaces? Well, we can have different notions of distance. We don't have to have the real numbers or the modulus function. We could have, say, m is equal to R2. So m is now 2-dimensional space. And the distance from vector x and vector y is going to be 1 if x is not y, so if x and y are not the same vector, and 0 if x is the same as y. Okay, so it's 1 if they're different, and 0 if they're the same. Can we show that this is in fact a metric space? Well, we can. Condition number 1, certainly the distance from x to y is greater than or equal to 0 by definition. We've defined it that way. Condition number 2, symmetric. Well, symmetry is obvious. I mean, if they're equal, then it's just 0, and if they're not equal, it's just 1, which is going to be the same even if you reverse the order. So that's certainly the distance from y to x. Good. Condition number 3, well, when is it 0? Well, it's 0 only when x is equal to y, so indeed the distance from x to y equals 0 implies x is equal to y. This is just from the definition. And number 4, triangle inequality, a bit trickier, but let's consider the distance from x to z plus the distance from z to y. Well, if one of these is 1, then we're done, right? Because the distance from x to y can be at most 1. So if either of these is 1, then it's certainly going to be greater than or equal to this distance here. So we're good there. The only other thing is if they're both 0. If they're both 0, then certainly we must have. So if both 0, then certainly x is equal to z is equal to y. Because if this one is 0, we have x is equal to z, and if this one is 0, we have z is equal to y. So altogether we get x is equal to y, and then that tells us that the distance from x to y is 0, because x is equal to y. So in all cases this will be greater than or equal than the distance from x to z. Okay, now this metric here, d, in this case, is known as a discrete metric. So just to recap here, M is the metric space, and D is the metric. Okay, so you may see M called a metric space, or the pair MD called a metric space, and D is referred to as a metric. So let me just recap this for you. I'll write this down and leave it on the screen for you. So MD is the metric space, and D is the metric. So D is the metric, the function is the metric, whereas M is the space itself. Okay, now I think that sums up all I wanted to say on metric spaces. If you have any questions about this topic, it is quite tricky at first, so if you have any questions, do feel free to ask in the comments section. Don't forget to subscribe for more videos. I'll be doing some further topics on metric spaces in the future. Don't forget to subscribe, and I'll see you next time.